right at the time I was starting my career here at UC Irvine, many of my friends had gone off to work in the pharmaceutical industry. The biotech industry was very hot. There was a lot of venture capital funding flowing into biotechnology companies, startups. There was a book published called The $1 Billion Molecule, and everybody knew about this book because it gave people an inside look about what it was like to be at a startup drug company trying to develop a new drug. And it is hard to invent new drugs that make it all the way to the clinic into human patients. And the book was called The $1 Billion Molecule, which is a little bit funny right now because now $1 billion doesn't seem like that much for pharmaceuticals. It's still a lot of money. And the point was that this company, the book was really about a company, Vertex Pharmaceuticals, that was really into this idea of rational drug design. You know, previously, the pharmaceutical industry for decades had been based on phenomenological pharmacology. You've got some frog model and you treat the muscles with drugs and you see if the muscle twitches or something like that. But now, around the 1990s, we started to have access to a lot of structural biology information, X-ray crystal structures of protein targets, or genetic information where we knew the genetic sequence. And so this is what was really driving Vertex. It's like, hey, we know the structures of these protease targets that are responsible for AIDS and hepatitis C. Why don't we try to design things that exactly fit into these pockets? They didn't really make a lasting drug, a $1 billion drug to target those proteases. But here's what brought this to mind. I was at on Tuesday, I was at this this little get-together that Vertex was hosting, Vertex Pharmaceuticals, and I ran into Sabine Hadida, and she is a rock star in the drug development industry. She was part of the team that developed Vertex's really true, super powerful, high-selling drugs. And so let's go ahead and talk about why Vertex became famous. They briefly had a drug they shared with another company that cracked $1 billion in sales for a year and then fell off the radar map. And so let's talk about what Sabine Hadida and her group did at Vertex. So Sabine's group, she's now head of chemistry at Vertex, was co-inventor of a molecule called VX-770. That's their investigational drug name when they're trying to keep it a secret. And that was eventually given the chemical name ivacaftor and was marketed as Kalydeco. Kalydeco or ivacaftor targets a protein that you may have heard about in your genetics classes or your biochemistry classes. It's the cystic fibrosis transmembrane conductance regulator, which is a stupid name, right? A chemist would never. It's a chloride ion channel that you find in your pulmonary epithelium. And so if this chloride ion channel is missing this phenylalanine, number 508, if you're born with that mutation, the chloride ion channel doesn't function properly. So you're not pushing chloride out of your lung epithelial cells, and usually water will follow. So if you're not pushing water out into your lungs, you have no way to cough up sputum, and your lungs fill with snot. You get bacterial infections, you die, and you don't live very long. And so the company decided, which is just crazy, that, well, we know there's this deletion mutation, and there's no binding pocket. There's no place where a ligand binds where we can look at the natural ligand or substrate and design something that looks similar. We're just going to see if we can find something that targets this mutation without knowing anything about how it would work. And they were able to find a set of molecules and optimize them to high potency that target this chloride ion channel. In fact, the drug turns out to fit in a very different place. And this is now what this drug and this family of drugs is used to treat cystic fibrosis around the world. And it keeps those people alive. So it's an amazing accomplishment in terms of targeting a class of protein targets that nobody thought anybody could ever drug. And her team did it. So really, the $1 billion molecule idea about targeting proteases didn't really work, but good pharmaceutical companies will find new targets and new areas, new therapeutic areas to make drugs. We've been talking about the chemistry of carboxylic acid derivatives, about carboxylic acids, acyl chlorides, esters, amides, how to interconvert them back and forth. And I just want to encourage you to take advantage of the many resources that we have for you. So right after lecture on Fridays, right after today's lecture, I hold study halls, so please come in and just practice studying. And if you have questions, you can ask me. Go to the study halls for the other members of our team, the teaching assistants. Take advantage of the peer tutors. Go to discussion section and practice working problems. It's a great opportunity to see how other people are approaching the problems and to get practice on the kinds of problems that I ask on my exams. And usually a little bit harder. The discussion section problems are a little bit harder because I don't want to give you questions in discussion section that are easier than the exam, because then you'll be surprised about what's happening on the exam. But the format's the same. And don't you want to get practice working the kinds of problems that I put on my exams? When everybody's right there to give you help. We have amazing learning assistants that are there to help each group of students think through the problems. Just a great chance to practice talking about science with your peers and how to solve scientific problems. That's what they do in the pharmaceutical industry. Try to fight complacency. It's another, couple of weeks before we have our exam that covers carbonyl chemistry, and you may think, oh, I got plenty of time. You don't have plenty of time. I mean, we are covering a lot of material. The carbonyl area is a big area, and you need to be on it this weekend, today, practicing problems. Next week, we're going to start a completely new set of material that's for our next exam. So either today or on Monday morning, we're going to finish exam 2 material, and you need to be an expert on that, solving every kind of problem. So take advantage of the resources we provide, work every problem you can get your hands on, problems in the book, problems that we give. Really, book problems is the most amazing and extensive resource that you need to tap into. Now, we left off talking about reactions of things like anhydrides and acyl chlorides, and midway through the book, we turned to the eponymous, carboxylic acids, the functional group for which this chapter is named. It's carboxylic acids. And so let's go and talk about, in the next few slides here, what are some of the reactions of carboxylic acids? And they are tricky. Carboxylic acids are probably the most complex in terms of reactivity derivatives of carboxylic acid derivatives. And here's why. If you take some sort of a powerful reactant and you put it in with a carboxylic acid, the problem is that anything that is powerful as a base is also powerful as a nucleophile. Anything that is powerful as a nucleophile is also powerful as a base. So if you think that you're going to take something like an alkoxide and try to fly in here and attack the carbonyl, that's not going to happen. What's going to happen is the fastest reaction here is to attack a first row atom, not a second row atom. And that first row atom is going to be the H, the acidic H. That's the fastest thing that always happens. So whether you add an alkylithium, whether you add sodium borohydride, whether you add a Grignard reagent, the first thing that will happen is that you're going to attack the carboxylic acid and turn this into a carboxylate anion, which is one of the least reactive, that is the least reactive carboxylic acid derivative that we have shown you. How are you going to attack a carboxylate anion when this lone pair right here is donating in and deactivating that carbonyl? I mean, that lone pair is right there 100% of the time. Very, very hard. We only showed you one reagent that can attack a carboxylate anion, that is lithium aluminum hydride. Yes, lithium aluminum hydride can reduce carboxylic acid derivatives. And we didn't tell you this, but that works because you heat it in order to try to drive those reactions. So this is a disaster. Carboxylic acids deprotonate and it makes them unreactive. So again, if you always look at this alternative process where, well, gee, I'd really like to attack this carbonyl, the problem is this is going to be slower. That's not going to happen. It's always going to deprotonate. So that makes carboxylic acids tricky. If you want a carboxylic acid to react, you can't solve that problem by just picking something that's more nucleophilic, right? Anything you do to make it more nucleophilic, you're simply going to make it more base, make it act as a base even faster. So what happens if we want to make new oxygen-carbon bonds? What happens if we want to make new bonds right here and we can't use more powerful bases? So if we want to make a new oxygen-carbon bond like this with this oxygen here, that's not a powerful enough nucleophile. So we need a new solution to this problem. Now let's go and talk about how you solve that problem. But first, we're just going to start covering reactions of carboxylic acids. What are things you can do with carboxylic acids? So the first reaction I'm going to show you is super important. And in order to get you ready to talk about this reaction that we mentioned as one of our recipes, I have to bring you back to your first quarter of organic chemistry when you were learning how to do SN2 reactions on alkyl chlorides. They taught you how to take alcohols, which you can't displace using SN2 reactions, and convert them into long carbon-chlorine bonds that are easy to do SN2 with. They're also easy to do E2 with. And the reaction that they taught you was to take thionyl chloride. SOCl2 is called thionyl chloride. And you had to add a base called pyridine. That pyridine base in there is used to soak up HCl, because you can't have HCl building up in these reaction conditions. So you get rid of the HCl by including pyridine, and the HCl turns into this harmless pyridinium chloride salt that you just remove in the aqueous wash. So you should remember that from chapter 9 in case you ever need to make an alkyl chloride in this class. Maybe you want to make a Grignard reagent out of that. Well, there you go. You make an alcohol into an alkyl chloride and then add magnesium, and you've got a Grignard reagent. All right, in this chapter, we're talking about carboxylic acid derivatives. And you can take carboxylic acids, which are not that useful, and convert them into acyl chlorides, which are massively useful. And as I've noted here, this is the most useful reaction in this chapter, in chapter 20. I have a typo there where I said chapter 22. But in this chapter on carboxylic acid derivatives, once you've got an acyl chloride, you can convert that into anything. Amides, esters, anhydrides if you wanted to. You could do Friedel-Crafts acylations from previous chapters, right? This is what makes this a powerful transformation. And the conditions look similar, but they are not the same. The conditions you use are thionyl chloride, SOCl2, but you don't use pyridine, you use heat, right? You do end up with HCl as a byproduct, but you can't add pyridine in there because the pyridine will react with the thionyl chloride. It'll deprotonate the carboxylate and do other stuff. The pyridine just is not compatible. So you simply just heat the reaction and allow the HCl to evaporate off. And you couldn't do that with the alcohol reaction. So this is the conditions. It should look similar to you. The functional group transformation replacing an OH should look a little bit similar. So I hope you won't find it too much trouble to memorize this powerful transformation of making acyl chlorides. All right, how do you get oxygen molecules to attack carboxylic acids? Boy, oxygen lone pairs, like these lone pairs right here, are just not very reactive. And the trick that we use is that we add catalytic acids. And there are two common ones. You could use others, but these are the two common ones that you'll see me use. Hydrochloric acid, you don't have to write the word catalytic, but it's a catalyst. It doesn't get incorporated into the product. It doesn't change the equilibrium constant. It just gets you to equilibrate between products and starting materials faster. So HCl is one common acid catalyst and sulfuric acid is the other. Not HBr, not toluene sulfonic acid. In theory you could use those, but these are the common ones that I would use. And again, all these acids do is they accelerate the rate at which you reach equilibrium. And the equilibrium constant for these reactions is 1 to 1. So if you just accelerate the rate at which you reach a 1-to-1 equilibrium, your yield will be 50%. I wouldn't consider that to be efficient. So we're going to have to talk about that. This is one of these things where how do you get a high yield of the ester? Well, the way you do that is that you use the alcohol. If you want to make an ester from a carboxylic acid, you use the alcohol in a large excess. That drives the equilibrium towards product, towards the ester. It's just Le Chatelier's principle. You should have learned about Le Chatelier's principle in freshman chemistry and general chemistry. So in order to make this a useful way to make esters, you have to use the alcohol solvents in a large excess. And then you throw away the leftover starting alcohol when the reaction's over. You just evaporate it off. That means it has to be a cheap alcohol if you're going to evaporate off the leftover alcohol. So there's only two alcohols that are cheap and easy to evaporate, and that's methanol and ethanol. And that's pretty much it. In theory, you could use propanol. In theory, you could use butanol. Nobody's going to do that. I would never do that. If the book says they're doing that, that doesn't make any sense. So really, this is a way that organic chemists make methyl and ethyl esters, because methanol and ethanol are cheap. So let's take a look at how I would expect you to write this if you're writing it as a transformation, like I've shown you here on the bottom. The way you would write this is you would write some sort of an acid catalyst. You could write HCl or H2SO4. You don't have to write cat for catalytic, but that's great if you recognize it's simply a catalyst. So for the catalyst, 10 times more catalyst, 10 times faster. So sometimes you actually use more than one equivalent just because you want it to be even faster. It's like, gee, I got to work up this reaction before I leave tonight, so maybe I'll dump in some more catalyst and get it to go faster. That's the kind of thinking you apply with catalysts. Okay, we need to show an excess of the alcohol, and there's two ways that you can do that. Here's method number one. I'll do this in dark blue here. One way you could do it is simply write, if you're trying to make an ethyl ester, is you write the alcohol as a reactant, and then you write the word excess. And if you leave off the word excess, this is incorrect. It's not efficient if you leave off the word excess. So if you write that as a reactant, you have to write the word excess. Or, if you want here, alternatively, right, the other alternative way to do this is, or you simply write the common solvent under the arrow. That means it's the solvent for the reaction. That's supposed to be a CH3. If you write a common solvent under the arrow, it means you're using it as the solvent. If I write it above the arrow, it means I'm using only one equivalent of that. So it's just kind of a convention in organic chemistry. There's one last thing you need to show, and the book doesn't show this, and for my exams, for my problem sets, you have to write heat here, because you don't get useful reaction rates unless you add heat. There are a few reactions that will go at reasonable rates at room temperature, and you don't have to show heat. And I'm not going to give you a list of 400 million reactions and tell you which ones require heat and which ones don't. But if you add heat, it will always work. It'll be fast. So it's a benefit to you that I don't make you memorize which ones require heat and which ones don't. Just always show heat, and it won't be wrong. All right, so I feel like this here is the most common way to write this: sulfuric acid or HCl, the alcohol under the arrow, and heat, delta symbol. That's pretty simple, and that's a way to make esters. You take carboxylic acids like this, you convert them into esters. And that's a common way to take carboxylic acids that aren't that useful and make them into esters. And once you have an ester, you can add Grignard reagents, you can do lithium aluminum hydride reductions, right? There's all kinds of things that you can do with esters. They can sit there while you do other chemistry. It's kind of a way of protecting carboxylic acids so they don't act as an acid anymore and mess up your other reactions. All right, and for some reason, I feel like students have a problem with cyclization reactions that make rings. But cyclic molecules are super important in pharmaceuticals, they're super important in natural products, they're super important in bioactive structures. And so I expect you to know how to take any of these reactions that I've shown you and have intramolecular versions of them. So here's an example of a problem. These are the kinds of problems I put on exams where I say, here's the product and here's the conditions, write the starting material in the box. Right? So I need to explain how I generate this ring. And if you look at the conditions, it's like, gee, okay, it's sulfuric acid and heat. That's what we call a Fischer esterification, that thing I showed you on the last slide. That acid-catalyzed ester formation is called a Fischer esterification. And this looks like an intramolecular version, and what you can see is missing is there's no alcohol under the arrow. Well, look at this. The alcohol here, the alcohol is attached. It's attached to this, 4-carbon chain with 2 methyls on it. And so in my starting material, it must be that the alcohol is attached. So let's go ahead and draw that out. So I'm trying to with high fidelity here, make sure that I've got, right? How do you do this without making a mistake? Well, one trick you can do is try to enumerate common carbon functional groups. So I think this is the right answer. Let me just double check. Let me enumerate carbon atoms, or not just carbon atoms, but carbon functional groups. I've got a CH2 group number here. I think that's the CH2 group number 1 over here. I've got a carbon over here that has no H's, right? Not just a carbon atom, but a carbon atom with no H's. Oh, look at that. I've got a carbon atom with no H's attached to carbon 1. And then my last carbon here before the oxygen is CH2 group number 3, and look at that. I've got a CH2 group number 3 right there. Right, this is called atom mapping, and it's a common strategy to make sure you didn't goof up translating starting material structures to products or it makes sure that you have a plan. If you're starting to write arrow pushing mechanisms, it's like, okay, can I see which atoms turn into something else in the product? That gives you kind of a plan for how to push arrows. I've got another atom right here. I'll call this atom B. You could use Mickey Mouse symbols, doesn't matter. Carbon atom B that has no H's on it. It's a carbonyl carbon. So, right, the new bond here is this bond. It's the bond you're making. And there is no way to write the word excess. The OH here is attached to the carboxylic acid in a 1-to-1 ratio. You can't add an excess of the bottom alcohol. So why is it that you don't require an excess? If you are making 5 and 6-membered rings, that means the OH, if it's 5 atoms away from the carbonyl or 6 atoms away, is colliding with immense frequency. This is the problem with organic reactions. Most reactants have to collide 1,000, 100,000, 1,000,000, 10 million times before you finally find a bond. Anything you can do to increase the rate of collision, like temperature, will increase the rate of the reaction. Because collisions are so frequent when atoms are 5 atoms, when atoms are 5 atoms away, that increases the collision frequency where you don't need excess to get good reaction rates. So when you're cyclizing, cyclization reactions to form 5 and 6-membered ring esters and amides are fast. They're fast. It's great. It's a great reaction to make 5 and 6-membered rings. Now, sometimes I'm going to give it to you like this. You're thinking, oh, that's easy. I get the concept. But I'm not going to write the starting material like this for you. The book doesn't do that. I don't do that. If you read the chemistry literature or research journals, they don't write the starting materials like that. They'll write it like this. Not because they're jerks, they're just trying to fit it into a short little space in their research article or in the book. Or maybe they're trying to write it out using typeset, like a text message or something. But when you write it out like this, it may not be so obvious that could cyclize around to a 6-membered ring. So you're going to have to practice this. Right? You're going to have to practice knowing that, yeah, of course, that can adopt all kinds of conformations, and one of them is going to be ring-like. And you're going to have to practice it enough to know that HCl or sulfuric acid with an alcohol and a carboxylic acid is a recipe for making esters. So how is it that I'm not going to make a mistake? Here's what I'm going to do. I'm going to count. I'm going to try to enumerate things. Maybe I'll try to use red here. This is oxygen atom 1. That's CH2 group number 2. Here's CH2 group number 3. Notice 2 is attached to 3, CH2 group number 4, CH2 group number 5. And then they didn't show you this, I didn't show you this, but that's a carbonyl group. Number 6 is a carbonyl. And I wrote it out CO2H. You need to know that that's a carbonyl group. You need to know the Lewis structure for CO2H. You have to have practiced so many times that it's totally obvious that's a carbonyl. So I'm going to arrange those so that they look like they're ready to form a ring. So I'm going to have to arrange these things. What should I put on top, the hydroxy or the carbonyl? Well, just like the top case, I'll try to draw the carbonyl on top. So if I draw the carbonyl on top, it's a carboxylic acid. I'll make that group number 6. And what's attached to number 6? CH2 group number 5. What's attached to CH2 group number 5? CH2 group number 4. What's attached to CH2 group number 4? CH2 group number 3. What's attached to CH2 group number 3? CH2 group number 2. And what's attached to CH2 group number 2? The OH. There we go. Let me just check. Boy, time's running out. We're taking an exam, but I'm still going to stop and check to make sure I didn't blow it. It's so easy to make a mistake, right? Don't gamble away your points by not checking. Finish your exam early and go back and check for mistakes. Let's check. Okay. Next to this CH2 group number 6, let's just check to make sure that I've got, or CO carbonyl group number 6. Let me check to make sure I've got a CH2 group number 5. There it is. Is that next to CH2 group number 4? Yes, there it is. Is that next to CH2 group number 3? Yes, there it is. Do I have one more CH2 group, number 2? Yes. All systems go, right? It looks simple, but you've got to take time to check your answers because it is easy to make mistakes. And these ring-forming reactions are going to seem complex until you've practiced a few of them, and then it's going to start to seem easy. And this idea of atom mapping you can also apply when somebody asks you, what's the mechanism for this? Well, you have to figure out which atoms in the starting material are the same atoms in the product. and figure out which bonds were broken and which bonds were formed. And mapping groups, CH2s to CH2s, carbons with no H's to carbons with no H's, is a good way to start if you have no idea what's going on, or if you're trying to double check yourself. Okay, carboxylic acid, you can make acid chlorides, you can convert them to esters, whether they're acyclic or cyclic, using acid catalyzed Fischer esterification. Let me show you another reaction that you can do with esters. Wait a second, we got to stop and talk about the mechanism for this Fischer esterification, this acid catalyzed hydrolysis. And I already explained to you, this is important. How do you get a lame OH nucleophile to attack this very unreactive carbonyl? That's not easy. You know, water and alcohols are not very nucleophilic. Sure, they can attack carbocations with only 6 electrons, but attacking a carbonyl with an OH next door, that's hard. So the trick is to use an acid catalyst, sulfuric acid or hydrochloric acid, and I'm not going to write HCl or sulfuric acid here because I don't actually know what's protonating this. Is it H3O plus that's protonating that? Or is it HCl? You don't know. You will never know. That's why we use symbolic for arrow pushing. For curved arrow pushing, we use this symbolic species HA, because you can't know what is the actual species that's putting the proton on this carbonyl. And once we protonate that carbonyl, this is now super easy to attack. That's not just a regular carbonyl, that's a supercarbonyl. And now, even a water molecule or an alcohol molecule can attack that carbonyl. Let me go ahead and draw that alcohol molecule down below. So if we were making a methyl ester in this case, could be an ethyl ester, could be an OH doing an intramolecular cyclization, doesn't matter. Now that that carbonyl is protonated, so easy to attack that. Wow, that's so easy. So easy to attack. We call that an oxonium ion when you have oxygen with 3 bonds. Like H3O plus is an oxonium ion. We don't have a special name that I know of for this oxygen double bonded, like a protonated carbonyl. I wish we had a simpler and obvious name for that. Now the next step of this reaction, notice how I drew this, sorry, let me go ahead and draw out the next structure for this. So the next structure, I've added to the carbonyl group. I've still got the OH attached from the carboxylic acid. And now I'm going to draw the oxygen nucleophile, but I'm going to draw the bonds because I've drawn this so many times, and you should too, practice this mechanism so many times, that you know you need to draw that HO bond. I know the next step is going to be that my A minus, which has been patiently waiting around, I know that the next step is that the A minus is going to deprotonate that H from the oxonium ion. And if you just write the H right next to the O with no bond, you're going to have to erase it or scratch it out or waste your time doing something. You need to practice this enough to know that, gee, I've got to take the proton off of this methanol, and I need to put that proton in a second step onto one of these 2 OHs. That's what's going to happen in the next 2 steps. We need to get the H off of here and then put it back onto one of these 2 groups. And that's how we're going to replace the OH. So we're doing addition. This first step, or this stage right here is called an addition step. And somewhere later in our 6-step mechanism, we're going to do an elimination. But there's all this proton transfer stuff going on. So let's go ahead and pull off the proton from our oxonium group. And that's going to leave us with this neutral tetrahedral intermediate. And it regenerates our acid catalyst. And watch, I've done this so many times, I know to put the acid on the top here. I'm kind of setting that acid right next to one of those OHs. Just dangling it there. It's so seductive. Look at that. We're just ready to protonate one of those. Now, it could reprotonate the methoxy group, of course, but that would just take us backwards. I'm not going to write the mechanism going backwards. It's kind of interesting, but we're trying to show how we go forward and remove one of these OHs. So here we go. We just attack. Whoops, let me use my red pen here. So now we're going to protonate one of the, it doesn't matter which OH, they're not distinguishable. So I'm going to do the top one. Just, I don't know, that just, it's arbitrary. And so now we've generated an H2O leaving group. It's an oxonium ion. And we're ready to push that out. It doesn't just leave on its own. This isn't like an SN1 reaction that you learned back in your first quarter of organic chemistry. The water's not just leaving, it's getting pushed out. Lone pairs on both the methoxy and the hydroxy group are pushing, both simultaneously pushing. That thing's gone. And the second you touch that with a proton, it is pushed out of there. Pushed out. Goodbye. And so now you end up with this intermediate. It's once again is an oxonium ion, 3 bonds to oxygen. It should look a lot like our second intermediate that we drew in this mechanism. And I've still got my A- floating around there somewhere. There must be something with a negative charge floating around. That's that A-. Notice how I draw it on the top here, so it's just ready to pull the proton off. Looks so obvious when I do it, because I practiced the mechanism enough to know where to draw the A- and the HA. I've just done this so many times, like you need to do it so many times. So you just need to practice that mechanism. Okay, and the last step, of course, is that we're going to remove that proton, and that gives us our ester product. So I'm not sure if I can fit that on the side here, but let me just draw it down here. It's a 6-step mechanism. Do you remember that when we talked about forming imines and enamines, it was a 6-step mechanism? Fischer esterification, turning carboxylic acids directly into esters with acid catalysts, is a 6-step mechanism. Hydrolyzing esters backwards to carboxylic acids involves exactly the same intermediates. All that changes is the arrow pushing. If I just erase these red arrows and use the same black chemical structures on here, it's the same. The intermediates are the same. There's not some secret mechanism to go backwards. It's got to involve the same transition states. All I change is the curved arrow pushing. So you need to practice that. I'm not going to take the time right here to redraw the backwards mechanism, but you need to know the mechanism for hydrolyzing esters back to carboxylic acids using a catalytic acid. And you need to practice that mechanism until it seems easy and intuitive. I expect you to know that mechanism, and every instructor who teaches organic chemistry expects you to know the mechanism for Fischer esterification. Enzymes that cleave esters, enzymes that cleave protein amide bonds are doing the same kinds of arrow pushing, the same kinds of elementary reaction steps. So, enzymes are confronted with the same types of chemical problems that you are when you try to sort out what needs to happen. Okay. Now, how do you take a carboxylic acid? You can take carboxylic acids and make acyl chlorides. You can make esters. And so now we're going to talk about making amides out of carboxylic acids in one step, in a single-step transformation. So let's suppose that you have a carboxylic acid like this and some sort of an amine, and you want to make an amide bond. Let's go ahead and highlight that new amide bond right here. There's the bond. Boy, that is super common in drugs like ivacaftor, or if you look at the top 200 pharmaceuticals, the small molecule drugs that they're making billions of dollars off of, most of them have amide bonds. So how do we do this? We do this very simply. There's a key reagent you need to know called DCC. That's how we do it. There you go. You can remember that. I mean, the only trick here is don't confuse it with PCC. If you write the D in some wishy-washy way and I can't tell whether it's a P or a D, I'm going to count it wrong. DCC. It doesn't stand for pyridinium chlorochromate. It stands for dicyclohexyl carbodiamide. Wow. And either NN dicyclohexyl carbodiamide or 1,3. But you don't need to know that. Thankfully for you, I don't expect you to know the chemical structure of this carbodiamide. I don't expect you to know the name of this carbodiamide. I just expect you to know DCC. So you need to memorize this. If you want to talk about an easy synthetic transformation to remember, this is an easy one, and it is an important one. Making amides is so important for drugs. And it doesn't matter whether the amine and the carboxylic acid are connected to each other or separate molecules. This is a powerful transformation. Right here, I can make an intramolecular, I can do this intramolecularly and make a cyclic amide. We call cyclic amides are called lactams. So you might have heard of beta-lactam antibiotics. Those have a ring, a cyclic amide in them. They're called lactam antibiotics. The only thing tricky about this is that there's no such thing as this species right here that I've drawn. If you put that into a flask, what would happen is that the amine, all the molecules, you put 10 to the 23rd of those molecules in the flask, what would happen is all the amines would deprotonate all the carboxylic acids, and this is the way this would exist, whether you're making a salt or whether you're putting it into solution, right? If you've taken a biochemistry class, you should have learned about this equilibrium, that amino acids don't actually exist as amino acids. They exist as Schwitter ions. So, so if I drew it like this over here, I would expect you to know that DCC will convert that into a lactam, right? There's no escaping that. You don't need to know the mechanism. You just need to know that amines and carboxylic acids, if you add them together, will form amide bonds. That's a very powerful transformation. And once you've got this amide bond, you can reduce the carbonyl down to a CH2 with lithium aluminum hydride. You still have the ring. You can reduce, you could reduce you can reduce the carbonyl here down to a CH2 group with lithium aluminum hydride, right? You don't break the carbon-nitrogen bond. Very powerful. You're starting to develop a whole set of transformations. So we're going to talk about this reduction of amides down to carbonyls, down to CH2 groups again when we hit the amines chapter. Okay, so you don't need to know the mechanism for this reaction. It's very difficult to remove the elements of water. You're losing the elements of water from this reaction, but it's not just water that you're removing. The water ends up generating a byproduct here called a urea. That's where the H2O went. You didn't actually form water in this dehydration. It's called a condensation process. Whenever you have the equivalent of water as a byproduct, you end up forming this very stable carbonyl byproduct called a urea. And it's insoluble. You just filter it off, and you got a pure solution of your product. Greatest thing ever. But you don't have to do the purification when you're taking my exams. You just need to write DCC. Okay, the book unfortunately shows you a reaction and doesn't explain why it's not useful to you, why it won't ever be useful to you. So industrially, one of the most important amide bond forming reactions is the synthesis of nylon. And this is the chemical structure of the polymer nylon. And you can see the key functional group in nylon is all these amides. Amide. There's more than one type of nylon. It just varies the way the amide groups are oriented. And the way they make this industrially is not using DCC. Somebody found that if you just take this dicarboxylic acid here, and you take this diamine, it will form amide bonds if you heat it high enough. So industrially, they're typically heating this to close to 280 degrees Celsius. This is Celsius. It's not like your oven temperature. This is 280 degrees Celsius. That is crazy temperatures. Most organic functional groups and molecules will fall apart at those temperatures. If you try to use this heating method on any of my exams as a way to make amide bonds, I'm going to count it wrong unless you're making nylon. That's the only example, right? What are the functional groups that can fall apart here? It's carbon-carbon bonds, CH2s. Those don't fall apart at 300 degrees. Any other functional group that is on your molecule will not be compatible with this. So don't use this. They shouldn't have taught you this. Why is this not a good method? Because if you take a carboxylic acid and you mix it with an amine, the first thing that happens is not forming amide bonds. The first thing that happens is the amine will deprotonate the carboxylic acid. Whoops, I wish I had drawn the bond there. And what that does when you mix those together is it turns the carboxylic acid into an unreactive carboxylate. That's the least reactive functional group in the carboxylic acid series. And it removes your proton from the nitrogen. That can't act as a nucleophile anymore. This is dead. So maybe if you heat it to 300 degrees Celsius, it might do something, but invariably this will give junk. Don't use this as a way to make amide bonds. It's not that hard to remember DCC. That would beautifully give this at room temperature, give these amide bonds. So don't think that this is general. This is just a way to synthesize nylon on an industrial scale. All right. This whole Fischer esterification, this idea that you can take carboxylic acids and you can take alcohols, and you can use catalytic acid and convert those into esters. That's called a Fischer esterification. But Fischer esterification is an equilibrium process. You're just driving the equilibrium forward. So that means you can drive the equilibrium the other direction and take esters and use the same conditions to hydrolyze them back to carboxylic acids. And all you have to do is change the equilibrium amounts of the species in there. So what would I do? I would take catalytic sulfuric acid, or I would take catalytic HCl. You don't have to write catalyst. I would take water, and I need to write the word excess if I want to drive the equilibrium, and then I would heat this. So instead of using excess methanol, I just use excess water, and that will drive this equilibrium in this direction now. Very simple. It's the same reaction as Fischer esterification. We don't call it Fischer hydrolysis for some reason. We just call it acid catalyzed hydrolysis, but it's the same idea. What if, as I've mentioned before, you don't have to write out water excess. If you wanted, you could just simply write H2O under the arrow. That implies that it is present in an excess, right? Simply writing water under the arrow. And that's typically how I would write it. I would usually not write water as a reagent. It's a common solvent, so I would write it under the arrow. So that's how you hydrolyze esters. Here's an example down below. This is aspirin, acetyl salicylic acid. So aspirin, you may know this. I think you might have done extractions of this or something. Contains an ester group. There's that carbon-oxygen bond of the ester. Very easy to hydrolyze this. Easy to hydrolyze this in your stomach. You have enzymes that are even faster. I just need to add some sort of an acid. How would I do that? This time I'll pick sulfuric acid. It could be the 0.1 molar hydrochloric acid in your stomach, H2O. Most of that passes through your stomach before it gets hydrolyzed, but there's some hydrolysis in your stomach. And if you heated this, this would be a very fast and efficient hydrolysis reaction. And the products of that reaction, in this case, would be salicylic acid. That's this. It's the phenol part, that's the alcohol part. And then as a byproduct here, we would get acetic acid. And that's the small part, the small molecule byproduct in this case is the carboxylic acid. It's a little bit unusual because the carboxylic acid is smaller than the alcohol part. But you could use this to hydrolyze these types of esters where the alcohol part is the bigger molecule if you wanted. All right. You need to know the mechanism for the hydrolysis of esters. It's the same intermediates as the formation of esters under acidic conditions, as I mentioned before. We just don't have time in the lecture to cover that. So know acid catalyzed esterification and hydrolysis backwards and forwards, an important transformation. All right, the last thing we have to talk about here in this ester carboxylic acid part is knowing how to, under mild conditions, without heat, hydrolyze esters. And this is super important. This is a more important way to cleave esters than using acid. And that's using base. Not just base, because base implies you're just interested in proton transfers, but hydroxide anion is a nucleophile. And the way we do this, and the reason why this is such a great procedure, is this uses sodium hydroxide, and it occurs at room temperature or below. I don't need to heat this. Lots of functional groups are unstable when you heat them. If you try to do everything using acid and heat, half your molecules are going to decompose and you'll get thousands of products. We love reactions that go at room temperature or 0 degrees or minus 78 degrees Celsius in organic chemistry. So this is a reaction. If you have ever felt solutions of sodium hydroxide and rubbed it between your fingers, not wearing plastic gloves, but using your fingers, it feels slippery. That's because this structure that you generate in this reaction is soap. So you're generating the sodium carboxylate over here. You're generating the sodium carboxylate of your carboxylic acid piece when you take long chains. And so you're converting the dead, your skin cells on the surface of your fingers are dead, but you're converting the lipids that are present on the outside of those dead cells into soap. You're churning your cells into soap. That's why it feels slippery. Sodium hydroxide isn't slippery if you're wearing nitrile gloves or something. It doesn't feel slippery at all. It's that fast. Just rub your fingers together with some sodium hydroxide solution. Okay, so let's go ahead and take a look at what's happening there in that reaction. Right, hydroxide anion is attacking here in this system. So hydroxide ion is a way more powerful nucleophile than water or than an alcohol. You don't need to protonate the carbonyl. In fact, you can't add acid to this reaction to protonate the carbonyl because it would just protonate the hydroxide. But hydroxide and alkoxides are so aggressive that they can easily attack an ester functional group. And so what's happening here is you're attacking that ester functional group, and then you make a tetrahedral intermediate. I'll just write R group here. And that tetrahedral intermediate then pushes out one of the two leaving groups. I'm not going to draw pushing out hydroxide because that just takes us backwards. Of course it could push out hydroxide. Of course that's happening half the time. But the other half of the time you push out the alkoxy group. And so that leads to these intermediates here. You get an alkoxide anion, you get a carboxylic acid, and those do an acid-base reaction. And we refer to this as saponification. Whoops, let me make that into a red arrow there. This process of hydrolyzing esters is referred to as saponification, and that means making soap. Now, the carboxylate anion, the sodium carboxylate, is only soapy if you have a long chain here. So we still call it saponification, even if it's a benzene ring out here, even if it's in some sort of just a short chain, if this is a cholesterol component or some other piece, we can still call it saponification, even if doesn't have soapy properties. But cleaving esters under mild room temperature conditions using sodium hydroxide is, we call that saponification. And so you don't typically want the carboxylate. I've told you before, in organic chemistry, we want neutral molecules that we can extract into organic solvents. You can't extract sodium carboxylates into organic solvents. Those are going to stay in the aqueous layer. So if you wanted to use this to make a carboxylic acid, if you wanted to use this synthetically to convert a carboxylic acid like this one, or a carboxylic ester like this one, into a carboxylic acid, we're going to have to protonate that carboxylate product. And the way you would draw this out is you would draw that out as sodium hydroxide is going to do the saponification to make a carboxylate anion, but you have to follow that up with an HCl workup. You don't have to write aqueous, you don't have to write workup, but if you don't write that out, then your product will be a sodium salt of that carboxylate. If I ask you to make a carboxylic acid, you need to have step 2, HCl, to put a proton on the carboxylate anion. So that's something you have to remember. There's another section in the book about lipid hydrolysis, right? That's the skin of your dead cells in your skin. Lipids are esters, so you can cleave that with sodium hydroxide. If you take fat, that's a triester. So take beef fat, stir it with sodium hydroxide, and you get soap. That's the way people used to make soap 150 years ago. They'd make their own soap out of animal fats, or you could use vegetable fats. Or if you've watched the movie Fight Club, they steal fat from the liposuction clinics and use sodium hydroxide to make soap and sell it back to these expensive clinics. Okay, I don't have time to cover the very last section of this. We'll pick up on that on Monday. I've got one last thing to tell you about how hard it is to hydrolyze amides using chemistry instead of enzymes. Brutal conditions. And then on Monday, we're going to be starting a completely different set of material that's for your next exam, exam 3. It's the next phase, the third part of this course we're starting. So, okay, weekend. This is the best, not next weekend, this weekend is your best opportunity to practice organic chemistry problems from the book, from any place you can get them. Practice solving problems. All right, I'll see you on Monday.